In today's lesson, we are going to be learning about molarity. Please make sure you watch this on either your phone or computer so you can take notes on your iPad. When any practice questions arise, I would ask that you pause the video and try and solve those on your own. Today we're going to learn about molarity. So what molarity is moles of solute per liter of solution. Now I know this word can seem confusing because we know so many different words in chemistry that start with mole. We'll talk about molecules and moles, and now we're introducing molarity. Again, molarity is different. So molarity will often be represented by this capital M here. What that M is equal to is moles of solute per, and it is always talking about 1 liter of a solution. The difference with this is how strong the acid itself is. So if we have 12 molar concentration HCl, that is a very, very, very strong acid. There is a ton of these acid molecules in that liter of solution. However, if we have a 1 molarity HCl, which is something you have worked with in class, that's much less dilute. So there's more water in there per amount of HCl. So realistically, this is going to have 12 times the amount of HCl molecules than this one will. In this question, it is asking us to calculate the molarity of a solution containing 6 moles of sodium hydroxide in 1.5 liters of solution. What I would like you to do is, using what you learned on the last slide, please try and do this one on your own. Now what I will do is give you a visual of what this problem is asking. So whenever you solve for molarity, you are solving per 1 liter of solution. Well, here we know we have 6 moles of NaOH in 1.5 liters. So if we had only 1 liter, how many moles would we have in that? So to give you an example of what's happening, on the right side here I have 1.5 liters of the sodium hydroxide solution, and in this total amount I have 6 moles of NaOH dissolved. So what's asking is if I take this and I were to have only 1 liter of it, so I can go through and fill this up to the 1 liter mark. So now at that 1 liter mark, how many moles of NaOH are in this solution? So in that video, the moles are all spread out between throughout the solution. So if I dump out 1 mole of it, it's still going to be spread out. You're going to get the same amount of sodium hydroxide per volume. However, we're just going to have less of it. So we take our 6 moles per 1.5 liters of solution, and we would find out that in that 1 liter of solution we would probably have about 4 moles of sodium hydroxide. So another way that you could write this would be 4.0 moles of NaOH, and that would be per 1 liter. In the next problem, I would also like you to try this one on your own. Please remember that molarity is moles per liter, not grams per liter. Alright, so now that you have tried this problem on your own, let's start with our 150 grams of copper chloride, and we need to convert that into moles. So 150 grams is a mass, that's an amount that we can measure, but moles are what we use, they're kind of the center of everything. That is what we use to determine concentration. So here we have 150 grams of copper chloride, and to convert that into moles we need to think back to last unit where we look at our periodic table. So we're basically just converting from grams of A to moles of A, and to find that we see that copper has a molar mass of 63.55 grams per mole, and chlorine has a molar mass of 35.45 grams per mole. And realistically we also have 2 chlorines in there, and you will see that we get a molar mass of 134.45 grams of copper chloride per 1 mole. So that means that in there we have 1.12 moles of copper chloride, and we know that molarity is equal to a moles per liter. So following our units, we're going to take the moles of copper chloride we have divided by the 3 liters of solution that we have. So it tells us that we have 3 liters of the solution is what that is dissolved in, and we see that we would create a 0.37 molarity copper chloride solution. What this would now look like is if we had 3 liters of water and we took our copper chloride here, or 150 grams of copper chloride, and we dumped it in there, it would, after it all dissolves and spreads out, we would go through and label this as a 0.37 molarity concentration of copper chloride. And please notice our sig figs in both of these answers that we did. We have 2 sig figs here because 150 is 2 sig figs as well as 3.0 liters. So that problem only has 2 sig figs. And in this problem, we also only have 2 sig figs, 6.0, 1.5, so our answer is 4.0 molarity NaOH. So this question is asking us how many grams of potassium chloride are in 2.50 liters of a 3 molar concentration KCl. So in this problem, it's really asking us, well, let's pretend we wanted to make 2.5 liters and we want a 3 molar concentration of potassium chloride. So what we need to do is, how many grams would I need to dissolve? How many grams of potassium chloride would have to go into that 2.5 liters? Well, molarity isn't talking about grams per liter, it's talking about moles per liter. So what we need to do is take our moles, or start with our molarity, and figure out, well, how many moles are dissolved in there? And to do that, we start with our 3 moles of potassium chloride, and we say that it is per 1 liter. Because remember, this capital M is the same as moles per 1 liter. So for every 1 liter of the solution, I have 3 moles in there. But if I have 2.5 liters, which is what it's telling me, we need to figure out, well, how many moles would be in 2.5 liters. So we multiply that. Our units are going to cancel out, so liters of solution cancel out with liters of solution, and we are left with moles of potassium chloride. And so in 2.5 liters, we would need 7.5 moles of potassium chloride. Then we are going to take that moles of potassium chloride, because we don't have a way to measure moles of potassium chloride, into an amount that we can actually measure out. Because remember, moles are a counting unit, whereas mass is something that we can measure. So we can't measure or count the number of atoms of potassium chloride. So we're going to convert that into grams. So we have 7.5 moles of KCl. And again, using our periodic table, we're going to see that potassium chloride has a molar mass of 74.55 grams per 1 mole. And that means we would need to dissolve 559 grams of potassium chloride into our 2.5 liters of solution to make a 3 molarity concentration. On this slide, we're going to talk about solution dilution, which is when you make a concentrated solution less concentrated. Because in the previous slides, we were talking about a solid, and we would take the mass of a solid, such as potassium chloride, and dissolve it in water. Well, when we're starting with a liquid, we're not going to measure that out as a mass. We're going to measure it in a volume. So we're going to use a different equation. An example of this is, say, your fingernail polish remover, which is about a 30% concentration of acetone. Well, the acetone that we order in is about a 60% concentration. So the way that you do that is, if you have something, here I'm just going to represent acetone with these purple dots. And now we take that 60% concentration and we pour in a bunch of water, and now we double the volume of it. Well, in this case, we didn't add more acetone. What's going to happen is all of these acetone dots are just going to spread out, and we're not going to get more acetone, but now it's spread out over a wider area. So therefore we diluted the solution, and now we would have only, say, a 30% concentration like your nail polish remover. Well, we do the same thing in class when we have acids. When we get acids from scientific companies, they often come in these jugs, and they are much, much stronger acids, such as this 12 molar HCl that we have here. So when I need to dilute those down for you, I actually use this equation. M1V1 equals M2V2. This equation is only ever used when we're provided molarity and volume. This equation can never be used when we have grams. This is specifically talking about a molarity and a volume. So what this tells us is, well, if I want to dilute down a solution, if I want to dilute down my 12 molar HCl into being a 1 molar solution, and I want to make 4 liters of that solution, I want to know, well, how much of that 12 molar solution do I need to dilute down using water? Because when I do this, I'm going to be taking some of this hydrochloric acid here, and I'm going to be pouring it, and we'll just pretend that this whole thing is 4 liters of volume. And I would only want to pour in a small amount of this 12 molar concentration in order to make a 1 molar concentration. Because what's going to happen is if I pretend that these green dots are my HCl, well, I'm going to have a ton of those in there, and as I start to add my water, like you saw with the acetone, those dots are now going to spread out, and they are going to start to fill the container here. And they're going to now spread out throughout the container. And they are going to be, and that is going to mean it's a less concentrated solution. If we go through and solve for this problem now, we are going to go through and we want to label our M1 and our V1. So in this case, I'm just going to say my 12 molarity is going to be my M1. And here it's asking how many milliliters of that do I want. So that will be my V1 because milliliters are units for volume. And this is asking, so how many milliliters of 12 molarity HCl are needed to make a 4 liter solution, so that will be my V2 of 1 molarity HCl, so that will be my M2. So when we plug that in here, we can see that we have our M1 times our X amounts of V1 are equal to M2 times 4,000 milliliters of second solution. So this is really a starting and a final product. So when we are doing this, please notice that the switch to 4,000 milliliters, that is the same as 4 liters because if we take our 4 liters, there are 1,000 milliliters, sorry, running out of room there, per 1 liter, and that will give us 4,000 milliliters. So we just put it in terms of milliliters instead. You could have left this in terms of liters, and then over here when you solve for this, you would be solving for liters. However, this question specifically asks us to solve for the amount of milliliters. So that is why we converted the liters here over to milliliters. And so when we do that, we just use algebra, and in this case we're going to divide by our 12 molarity, and sorry, things got a little crammed in here. We divide by our 12 molarity, that's going to cancel out. Divide this entire side by 12 molarity, and you'll notice that our units of molarity cancel out with molarity, and we are left with units of milliliters. And when we do that, we get a final answer of X is equal to 330 milliliters. Now what that is telling me is in our beaker here, I would first have to add in I would first pour 330 milliliters of my strong acid into that 4 liter beaker, and so that would fill up, to a line of about right here. And then I would top the rest of that off with water to fill that remaining amount up to the 4 liter mark, which would be equal to about 3,600 370 milliliters of water, because 330 milliliters of acid that I added plus the 3,670 milliliters of water would give me my 4 liters of desired solution. After I go through and do that, that is going to start to mix around, and that's why we want to shake the solution, so that way the strong acid that I have down here is going to mix around, which is represented by the green dot still, and that 12 molar solution that we had in the jug here is now diluted from all of the water that we added in, and we are going to be left with 4 liters of a 1 molar concentration of HCl, which is what we wanted.